Hey, everybody, this is Larry. Happy New Year 2021. Oh, what a year that was, huh? Uh, January 1st. This part is the same. Hope you had a Happy New Year, of course. Going to do these me solving every day for in January. I've done them every day since April, so I guess that's like 8 months or something like that of problems. So let me know what you think. Hit the like button, hit the subscribe button if you want to keep on going and do this year with me. And yeah, and join me on Discord. So if you have any questions, it's easier to ask and answer there. Cool. So let's get started on this new year. Check array formation through concatenation. So I usually solve and explain these problems live, meaning that I only see them here now for the first time. So the flow may be a little bit weird, but walk me through it and fast forward if you can or need to, or just skip ahead. Let me know what you think about this format because I think it's at least different from everyone else. But yeah, okay. So check array formation through concatenation. You're given an array of distinct integers R and an array of integers array pieces where pieces are distinct. Concat them in any order, cannot reorder. Okay, A5, AA1. Okay, so you have to do them in an order. Trying to understand how the concatenations work with respect to like, maybe I'm just misreading this a little bit. With respect to just like, like if there's a pieces that is 46 and 4, does that match this or is it just unique? Okay, I guess maybe it just has to be naive. Okay, so I think this is straightforward-ish to understand. I mean, though it is a little bit awkward, but basically what my initial plan and just strategy after reading this is just go from left to right and then greedily find them in pieces. Of course, if you do them in a inefficient way, the complexity may be kind of bad. Note that, however, in this case, n is small, n is less than 100, so you can probably get away with it, but I would recommend just doing it in a good way. And if you watched me try to do these kind of problems in a contest setting, that's when I optimize for solve time, right? But if you're doing an interview, you're not optimizing for solve time, you're optimizing for correct complexity or close to optimal complexity and being able to explain it and solve it, obviously, and coding it up. So in those scenarios, I would definitely try to upsolve it as much as you can. Okay, so for this one, as we said, I think it is just greedy going from left to right. But of course, you will have to, it becomes an implementation problem and data structure problem. For this, I think it's sufficient to, because, yeah, you cannot reorder the integers in each piece inside each subpiece, and you have to do them in that order because you cannot reorder it. So in that sense, you can greedy through it. And the way that I would do that is just instead of having a linear scan every time, you could just use a hash table on the first element so that you're looking at it. There are different ways of visualize, to visualize this problem. And the way that I think about a lot of these problems is just using graph theory. It may not be your way of thinking about it, but for me, it's just thinking that's the way that I think about it. Where okay, there's in this case there's a 91. That means that there's an edge between the left and the right of this node. For this 4 and 64 means that there's an edge between the left of here and right of here. And the other key thing to notice in this problem, which you may assume to be correct for greedy, which is true for greedy, but it's kind of like the inverse thing, right? Where like you may not think it works for greedy, but because of this constraint, it actually does work for greedy, which is that it is distinct. If they were not distinct, then you can imagine a case where all of them are ones or something like that, and you have to figure it out how to kind of combine them, and then it becomes a dynamic programming problem at best. At worst, it will be NP, right? Because you could probably reduce it to one of the Helm cycles or something like that, or Helm path rather. But in either case, yeah. So Cool, cool. So yeah, noting that this is this thing and that we are not allowed to reorder, and this is actually a cool condition in that if you are allowed to reorder it, it actually makes the problem harder. So this is definitely a problem where the constraints makes it easier to solve and let it to be greedy about. So it's kind of, you know, when you upsolve these and you look at these variations, definitely keep those in mind because, well, you know, as I said, like just very subtle things will make the complexity way different, and because you cannot prove certain invariants for greedy or the suboptimal subproblem to be true. Okay, or the sorry, not suboptimal subproblem, optimal subproblem. Okay, but yeah, with all that said, what I'm going to do is just, as I mentioned, hash, you know, by the first element because every element is unique, and so we are able to look up the first element, then we know that it is the beginning of a piece and so forth. So I'm going to do that. And right now I'm just struggling a little bit on naming things, but let's start with naming this n because that's just my convention. And then for each piece, for piece in pieces, as we said, we should have a collection that let's just have a lookup dictionary, right? So I'm gonna call it lookup. I don't know if that's a great name. Probably not, to be honest. But yeah, but lookup piece of 0, as we said, we hash by the first one because if it doesn't make sense to make by a middle one because you cannot reorder it, so that you cannot unlock the 64 in this case before using the 4 anyway, right? So that, like I said, there are a lot of conditions that make greedy possible in this problem, correctly or not. So yeah. And note that here I might debate using like a queue or something, or a deck in Python's case, but it's just your preference whether you want to keep track of the index or not. So actually I'm going to do that here, so that makes it a little bit clearer, but you can also just keep track of an index going from left to right, so I don't think it matters that much. But yeah, so here I'm just going to index. It's probably not a great name in this case, but yeah. So then now, while index is less than n, I do something, okay, right? So then now we look at the first lookup table. Okay, so if index not in lookup, then we return false. That means that there's no path to it, or if this number is in pieces, it's not in the first element, right? And then now, we can do something like while lookup index. Oops, no, sorry, I messed this up a little bit. The element is not in lookup. Yeah, obviously. I mean, I think hopefully that makes sense. This change is what I meant to do, but I just whoops. But yeah, so while this thing, okay, let's actually change this a little bit. So current element is equal to this. So let's change that a little bit because we might want to use it, because this is the lookup key. So while maybe better name is key. Sorry about the indecisiveness. Usually I give it more time to think, but like I said, I usually record these live, so then, you know. But yeah, so while the length of this is greater than 0, oops, how did that happen? Greater than 0. So then now we want to go piece by piece, matching it, moving it. You can think about it as 2 pointers, though it's not 2 pointers in the same way as sliding windows. It's just a pointer in array and a pointer in lookup key, which is a deck. So yeah, so then now, while this is true, if array of index is not equal to the lookup of key dot the first element, then we return false, right? Because that means that the first 2 elements are not of the 2 lists that you want to match are not matching up. And then okay, so then now if they do match, then what do you want to do? Well, you increase the index on the array side, and then you also want to pop off the left, pop off the deck. So this is just lookups of key dot pop left, right? And now because we do an index plus or minus 1, we should put it here that if if index is greater than or equal to r sub index n, I guess we already declared this, or this, we return false. And because this is, if we're at the end, actually, is that true? Let's see. I actually don't know what we do with extra elements, so maybe I'm wrong on this one. Okay, so then maybe we could do another one where if index is equal to n, we return true, because that means that we went through the entire way, even though there may be extra elements in lookup, the current lookup chunk, right? Of course, this may, it's not super clear. It's not super clear whether this should be true or false, because I don't know if you're able to trim, if you want to call it that. So this may, this is a base case that depends on the interpretation of this problem. And I think actually maybe you don't interpret it that way, but I'm gonna leave it like that. But it's an easy fix if it's not, and we'll test it later. Well, we'll test it later, but I want to put the test now before I forget. So we want 1, 2, and then in the key, which is 1, 1, 2, 3, because then now the 3 is extra, right? Yeah, so let's run the code real quick. It may not, yeah, ooh. Did I mess that up? Oh, did I have them in the wrong order? No, oh, whoops, I just have missed. Actually, I'm not gonna run this now because it might not terminate because I didn't finish the code. But yeah. And then now, of course, as I always say, the loop invariants are kind of how these if statements fit together in a way that you convince yourself that at the end, this, for example, this still has one element and index is less than n and so forth. So that way n, if we ran out of element, if we, this loop ends with index is equal to n, which is what we want to return true. So then we can just return true. Is this it? Yeah, maybe. I think so. So let's yeah, let's give it a one code. Expected rows of pieces that, oh, they're only 1 or 2. Okay. So basically, this is saying that the sum of the pieces is equal to r of length. So actually, I missed this constraint altogether. So, and what I mean by, so what practically happens is that this will never happen. So yeah, this should never happen in any case. So yeah, okay. So I didn't even, okay. I mean, this should be true now, hopefully. Okay, well, I was going to say, but once time limit exceeded, then some of our preconditions are not right. So now I think this is mostly right. So let's put all the test cases in. This is where, you could fast forward a little bit if you like. This is like the training montage where there's, live music, Eye of the Tiger or something playing. It was like, while I, speed through this. But in real life, I guess we don't. But yeah, and there's no magic to it, as you can see. I am literally just, doing this manually, because I am as time conscious as you are as well. Okay, so that looks good. Let's give it a submit. Actually, I don't know if the zero element a thing. No, so okay, so let's give it a submit. Okay, cool. Yeah, so one thing that I would also say is that usually I talk about I think about complexity before submitting, but in this case, like, I don't, because I know it's linear. Why do I know it's linear? Well, even though the 2 while loops, because you may say, okay, the 2 while loops, so it's probably n squared, right? But the thing is that, and we kind of alluded to it a little bit with the 2 pointers thing, but the short answer about how to figure this out is that for each cell, for each element in an array, we only look at it once, right? Because, okay, we do this lookup, and then here, this happens only once per element, right? So, and all these other stuff is constant time. So in a way, because each element takes constant amount of time and you have n elements, this is going to take O of n time, which is linear time, right? So yeah, and in terms of space, you have that same analysis where each element, it's only going to be in take up one space in this lookup table, so it's also going to be the O of n. You could, as I said, you can probably do it without it, and if you're really clever, you don't need this linear extra linear space, so because this is linear space for sure, you can do something funky, and this is a good upsolving opportunity to make it all one space by maybe having this point to the index of in pieces, and then you go you keep another variable to keep track of stuff in pieces. The reason why I did it this way is just so that for explanation purposes, it's more clearer to do it this way versus another index variable declaration, which is another for loop and something like that. I think so. I don't know. Let me know if you agree with that. But yeah, but it is possible to do it in constant space or constant. Yeah, yeah. That's pretty much all I have. Linear time, linear space. But as I said, you can upsolve it to constant space if you like. Yeah. So first problem of the year. Let me know what you think. Yeah, that's all I have. So yeah, hopefully that's a good way to start off the year. Hopefully you have a great year as well. Last year was rough in general, obviously, but happy new year, and I will see you later. Bye bye.